Hello everyone. As always, I encourage you to pause the video, read the problem, and then look for the solution. So getting right to it, for A, the term definite volume applies to both solids and gases. That is true. Both solids and liquids have a definite volume. For the next one, thermal expansion of a liquid is generally greater than that of the corresponding solid. Again, that's usually true as well. Thermal expansion for a liquid is generally greater than the corresponding solid. The next one, the compressibility of a gas is generally less than that of a corresponding liquid. That is false. Gases are easily compressed and expanded. And the last one, the density of a solid is about the same as the corresponding gas, and that's also false. The density of a solid is much greater than that of the corresponding gas. For this slide, we're trying to indicate the state of matter to which each of the following characterization applies. For A, disruptive and cohesive forces are about the same magnitude, and we're looking for the liquid state in this case. Letter B, disruptive forces are significantly less than the cohesive forces. We're looking for the solid state in this case. Kinetic energy dominates over potential energy. We're looking for the gaseous state. Particles are moving extremely fast in random motions. And for D, the kinetic energy is significantly less than the potential energy, and for this one we would be looking for a solid state. Not much kinetic energy moving. Those molecules are very, very stationary, maybe vibrations taking place. For these problems, we're trying to use the gas laws in order to figure out an unknown. So in this case, we're looking for the number of moles. That's going to be symbolized as N. Occupy a volume here, that's volume, and a pressure of 2.8 atms. So that's pressure. And a temperature of 298 Kelvin, so that's our T. When we have moles, anytime we should be using PV is equal to nRT per minute. That's our ideal gas law. And here we're going to try to isolate N, so we'll divide by R and T on both sides. And then it's just a matter of plugging your numbers in and crunching out the numbers. However, you have to be aware that R is equal to, when we're working with atmospheres, 0.0821 is our constant, and the units are atms times moles over liters times kelvins. So plugging in those numbers, this is what you would get: 11 moles of your gas. So in the second one, a balloon is filled with 35 liters. That's our volume of helium in the morning when the temperature is 20 degrees. So right off the bat, we're going to add 273 to that to get us into Kelvin. That will be temperature. By noon, the temperature is up to 45. That's going to be temperature 2. And we're looking for what is our new volume. So we're looking for volume 2. This would be an example of Charles's law. It looks like this. And we are looking for what is volume 2 over here. So just cross multiply the T up to the top and then plug your numbers in and solve. Doing that just like I did, but plugging in the numbers, you'd end up with 38 liters. For the third problem, a balloon can hold 85 liters. That's our volume of air is inflated with 3.5 moles. That's our N. Of a gas at a pressure of 1 atmosphere. So pressure, what is our temperature in Celsius? So anytime you see moles, you should be thinking PV is equal to nRT. I like to rearrange equations. So I'm going to divide out N and R on both sides. Divide by N and R. And then it's just a matter of plugging in your numbers. Again, we are working with atmospheres, so we're going to use this ideal gas constant up here. Plugging in the numbers, you'll end up with 296 Kelvin, and then you should subtract 273 from it to get your desired temperature in Celsius. Looks like some more gas law problems. So in this case, we have an internal pressure of 1 atm and a volume of 4.5 liters. That's our volume, and it's at 20 degrees Celsius. So again, add 273 right off the bat to get it into Kelvin. That will be temperature 1. What volume would the balloon occupy at an altitude where the pressure, that's pressure 2, and our temperature 2 in this case is going to be negative 20 degrees, but we're going to add 273 to it. So this is going to be the combined gas law, which looks like this. These are our initial conditions. These over here are our final conditions. And we're looking for what volume. So we're going to multiply temperature, cross multiply up. Bring pressure 2 down, and that gets you volume 2 all by itself. Plugging in those numbers, you end up with something that looks like this right here. About 6.48 liters will be your answer when you're done. Alright, last problem on this slide. So we have 6 liters of a gas in a piston at a pressure of 1.0 atm are compressed to a new volume of 3.5. What is our pressure inside? So we're looking for pressure 2. These are our initial conditions right here. This would be another gas law. PV is equal to PV. These are initial conditions. I wrote those in the wrong order, sorry about that, but it doesn't change the fact that we can still solve for our new pressure just by dividing out volume 2. Plugging in our numbers, we would end up with 1.7 atm. Notice the liters canceling, so always double check your units. I should have been doing that the whole time. Looks like a couple more gas law problems. So the initial volume of a gas at a pressure of 3.2 atms is 2.9 liters. What will be the volume if our pressure is increased? So this is pressure 2 to 4 atm. So we're looking for a V2. Same equation as last time. These are my initial conditions. These are my final conditions. Solving for V2, I just divide out pressure 2. And then it's just plugging in your numbers and crunching the numbers, watching the units fall off. Make sure your units are always good there. Alright, last one on this page. An airtight container with a volume of this has an internal pressure of 1, so that's our pressure, and an internal temperature of 15 degrees. So again, add a 273 right off the bat. Get your Kelvin, that's temperature 1. Is washed on the deck of the ship and sinks to a depth of 175 atm, so that's pressure 2, to a temperature of 3 degrees Celsius. So again, add 273 right off the bat. That will be temperature 2. What is the new volume? So again, this will be the combined gas law, which looks like this right here. On the left are my initial conditions, on the right are my final conditions. And now we have to solve for volume 2. So again, cross multiply T2 up to the top and pressure 2 down to the bottom. That gets you volume 2 all by itself. Now you can always plug numbers in, do the math, simplify it, and then divide last. I like to just rearrange the equation. That works best for me. Watching the units drop off here. ATMs go away. Kelvins go away. The only thing we have left is liters for our units, and you end up with 233. This looks like a little bit of Dalton's law of partial pressures. So we have a total pressure exerted by a mixture of oxygen, nitrogen, and helium gases as 1.5 atm. We're looking for the partial pressure of oxygen, given that the partial pressure of nitrogen and helium are these two respectively. So our formula is pressure total is equal to pressure 1 plus pressure 2 plus pressure 3. You could say that the first one is oxygen, the second one is nitrogen, and the third one is helium. It doesn't really matter. So I'm just going to plug the numbers in. 1.5 atm goes here, equals pressure 1, which we'll say is 0.75, plus pressure 2, which is 0.33 atm, plus pressure 3 in this case. So you can see, hopefully, all you have to do is really subtract the 0.75 and the 0.33 from the 1.5. And when you do that, you end up with 0.42 ATMs. Next one, number 58. The total pressure exerted by a mixture of helium, neon, and argon is 2 ATMs. What's the partial pressure in atmospheres of neon given partial pressure of the other two gases are both 0.25? So it's the same equation. Again, you can label 1, 2, and 3 as your gases, but it's not going to affect your answer. So all the gases are 2. And then it's going to give you 2 of the pressures, 0.25 ATMs, plus another 0.25 ATMs, plus your third gas. So just subtract 0.5 really from 2, and you end up with your answer, whoops, sorry about that, of 1.5. And the last one, 7-59, gas contains oxygen, nitrogen, and argon at partial pressures of 125, 175, and 225 respectively. If CO2 is added to the mixture until the total pressure reaches 623 millimeters of mercury, what's the partial pressure in millimeters of mercury of the CO2? So in this case, it looks like we have 4 gases, and we're going to subtract 3 of them from our total pressure. So our total pressure in this case was a 623 minus all the other pressures that were given, 125 minus the 175 minus 225, and those are all in millimeters of mercury, so your answer turns out to be 98 millimeters of mercury. These are more conceptual questions. How does the increase in temperature of a liquid affect the rate of vaporization? Hopefully you'd say that. As the temperature goes up, the rate of evaporation is going to go up, so it increases. Next one, how does the increase in surface area of a liquid affect the rate of evaporation? Hopefully say more surface area, more evaporation, so it increases. Another conceptual question, what is the relationship between the temperature of a liquid and the vapor pressure of the liquid? And looking at the answer, the higher the temperature, the higher the vapor pressure. Direct relationship there. For this particular example, we're looking for what type of interactions, intermolecular forces will be taking place. For dipole-dipole, we're looking for a positive and negative end of one molecule. For hydrogen bonding, we're looking for H being kind of bonded to an F, O, or N, and London forces are always present. So with hydrogen, when it's bonded, there is no hot positive or negative end. There is no F, O, or N. This is just London forces. For this one, there could be a hydrogen bond between the H of this molecule and the F of that molecule. So there is hydrogen bonding taking place, and there's always London forces taking place. For C, carbon monoxide, this is a polar molecule. So we have a slight negative and a slight positive. So when another carbon monoxide molecule interacts, there's going to be a slight attraction between the negative and the positive ends of opposite molecules. So there is some intermolecular forces, dipole-dipole, and London forces. F2, it's kind of a lot like our first one. It's a very nonpolar molecule. There is no positive, negative end to this particular molecule. So really all we have at play here are London forces. In which of the following substance in the pure liquid state would hydrogen bonding occur? In order for hydrogen bonding to occur, again, you need F, O, or N to be taking place, and And in this one, the H is bonded to the C, not to the O, so no hydrogen bonding taking place. On letter B, yes, there will be hydrogen taking place because of the N that's exposed here. In C, again, yes, there will be hydrogen bonding that could take place because of that exposed oxygen right there. And on the last one, HI, no hydrogen bonding. H is bonded to I, so nothing on that one. Thanks for watching. Hope it helps.